Hello students, good morning. Today I am going to take alpha beta pruning algorithm. So what is alpha beta pruning algorithm? It is an optimization technique for minimax algorithm. Minimax algorithm already I have taken in the last offline class, right? So I hope you all know what is minimax algorithm. And alpha beta pruning algorithm is the optimization technique for minimax algorithm. This alpha beta pruning algorithm, prunes means cut off, removing branch of the game tree that will never affect the final decision. That is, it will remove the unnecessary branches. Okay, unnecessary branches and increase the speed of searching. And alpha means I always take the highest value, and the initial value of alpha is minus infinity, and maximum player only can update the value of alpha. Beta means lowest value, initial value of beta is plus infinity, and minimum player only can update the value of beta. Condition is always alpha greater than or equal to beta. This algorithm explores only the most promising branches of game tree while discarding unnecessary branches. Okay, it will take only the promising branches and remove the unnecessary branches. Okay, minimax is a decision making algorithm which is used in two player games where one player maximizes their outcome and the other player aims to minimize the outcome. The maximize player always try to maximize his probability of winning the game and minimize and when the minimizing player always try to minimize the possibility of maximizer. Okay, so it is a fundamental concept in game theory and artificial intelligence, and it's a diagram of the alpha beta pruning algorithm. Maximizer move, minimizer move, again maximizer move, and it will go on. The last one is a terminal node. So in game tree, each node represents a possible game state. Each and every node represents the state of the game, and each branch represents the moves of the game. Okay. Now what is alpha beta? Alpha represents the best score that a maximum player has found so far in the particular branch. It is the highest score the maximum player can achieve up to this point. And what is beta? On the other hand, beta represents the best score that the minimizing player has found in his specific branch. It is the lowest score the minimum player can allow up to this point. Okay, and beta tracks the minimizes best known option. At the beginning of alpha beta pruning process, we set the initial values for both alpha and beta. The initial value of alpha is the minus infinity, that is the worst possible score, and the initial value for beta is the plus infinity, that's the best possible score. Okay. Question. The question will be like this. Consider the following game tree where the maximum player is the root and the values at the terminal nodes represent the utility values. For example, 1, 2, 5, 7, 0, 1, 6 and 4 are the utility values of the nodes at the terminal node. Perform minimax search on this tree and determine the optimal value at the root. Apply alpha beta pruning algorithm to the same tree. Show the order of node exploration. Indicate which branches are pruned. Write down the values of alpha and beta at each. This is the question. Okay. Now it's a game tree. Okay. See the game tree. First node, first A is a root node, B and C are child node of root node, D, E, F, G are children nodes of their parent node B and C, and the node H2O is the terminal nodes. Okay. So see the game tree. Now, first one. Here in this alpha beta pruning technique, we are using the depth first search technique. Depth first search, not breadth first. We are following the depth first search. So depth first search, we should move in the left side of the tree. So move in the left side of the tree. While moving left side, just traverse from A to B. The initial value of A just transfer to B. So alpha equal to minus infinity, beta equal to plus infinity. Then move from B to D. So the initial values are alpha equal to minus infinity, beta equal to plus infinity. Just the initial values are traversed here also. From D, You can assume like that. It is the chance of the maximum player to move in the game. Okay. Max min max. See the graph. Now it is a time for maximizer to move the coin. Okay, or to play in the game. You can take like this, to play in the game. Now how he can play? He has to compare its minimum value minus infinity with the utility value of the node h. It has to compare its initial value minus infinity with the utility value of the node h. Compare which one is maximum. Minus infinity 1, which one is maximum? 1 is the maximum, right? See, 1 is the maximum. Okay, so put 1 here. Then compare this 1 with the utility value of node I. What is the value of node I? 2. 1 and 2, which one is maximum? 2. So put 2 here. So here now the node value of the node D is 2. Okay, put 2 here and put the node value of D also 2. Okay, and next one. Now update the alpha value to 2, because 2 is the maximum. So alpha is updated to the value 2. Now we are going to the previous depth level. That is, we are going to the depth of minimizer. Backtracking. Depth of minimizer always do the minimizing value, right? Minimizing work, right? So now compare what's the value of beta there? Plus infinity. What's the node value of D? 2. So compare and take the minimum one. It is a minimizer's move, right? Now compare the initial value of beta with the node value of D. Node value of D is 2. So which one is minimum here? Which one is minimum? Plus 2 and infinity. 2 and infinity. Which one is minimum? 2. So take 2. So the node value of B is 2. Okay. And update the beta value to 2. Now the beta value is updated to 2. And now see, who is the child value who is the another child of B? E. Node E is the another child of B. So come here. Just the values are just transferred to E here. Alpha equal to minus infinity, beta equal to 2. Okay. Now it is the time for maximizer's move. So compare maximizer alpha. Compare the minus value of alpha with the utility value of the node J. Which one is maximum? Minus infinity or 5? 5 is the maximum. So put 5 here. Okay, and update alpha equal to 5. Alpha equal to plus 5. And put 5 as the node value for E. The node value of E is 5. Now check the condition. Alpha greater than equal to beta. What's alpha value? 5. What's the beta value? 2. 5 is greater than 2. So no need to traverse from E to K. No need to traverse from E to K. No need, because condition is satisfied. See, condition is satisfied. So no need to traverse from E to K. Then go backtrack. Go backtrack to B. Now it's the time for minimizer's move, right? So minimizer beta. Beta means minimum. Compare beta value 2 with the node value of E. What is the node value of E? 5. 2. So compare 2 and 5. Which one is minimum? 2 is the minimum. So leave as it is. Put 2 here. Leave as it is. Okay. Then go backtrack. Now go backtrack. B to A. Backtracking. Now backtracking. A is the now here maximizer alpha. So it is time for maximizer to move, right? So now compare what is the value of alpha here? Minus infinity. Compare minus infinity with 2. Which one is maximum? 2. So put 2 here. So put 2 here. Okay. Then 2 is the sign of A, C. So come here. Just transfer this value to C. Then take left side. We are following depth first search, right? So take left side. Left side means C to F. So the transfer this value alpha into beta is to transfer the value here. Now maximizer depth level is maximizer. Now is the time for maximizer to move, right? So maximizer alpha into compare alpha with the utility value of the node L. Compare alpha the utility value of node L 0. So which one is maximum, 2 or 0? 2 is the maximum, leave it. Then compare 2 with the utility value of M. Which one is maximum, 2 or 1? Again 2 is the maximum. So no change. So no change. But anyhow we have to find the node value for node F. So compare this one 0 and 1. Which one is maximum here? 1. So put 1. So 1. 1 is the node value of F. Again backtracking. Here again go backtracking, again go to node C. Now it's the time for minimizer to move, right? So what is the minimum? What is the value of beta? Plus infinity. What is the node value of F? 1. So here we have to take the minimum value plus infinity 1. So 1 is the minimum. So put 1 here. Now check the condition. Alpha 2, beta 1. So 2 greater than equal to 1. True. Condition is satisfied. Here condition is satisfied. So no need to traverse from C to G or G to N or G to O. No need, because condition is satisfied here. So go backtracking from C to A. Now it's a maximizer's move, right? What is the maximizer's value? Alpha value here 2. What is the node value of C? 1. So compare 2 and 1. Which one is maximum? 2. So leave it. That's all. Maximum. Now take the same nodes with the same value. So node A has the value 2, B has the value 2, D has the value 2, and I has the value 2. So this is the shortest path. A to B, B to D, D to I is the shortest path. So shortest path is A to B, B to D, D to E. That is A equal to, B equal to, D equal to, I equal to. Okay, we are taking nodes with the same value. Okay. Applications of alpha beta pruning. Alpha beta pruning is widely used in AI applications for two-player games such as chess. Enhances the efficiency of chess engines, allowing them to evaluate deeper moves with time constraints. So we are using alpha beta pruning algorithm in the chess app. Checkers. There is one games like checker. In that games also we are using this alpha beta pruning technique. Checkers optimizes move evaluation in checkers, making AI opponent more challenging. And another one is Athella improves decision making process in Athella, leading to stronger AI strategies. Conclusion: alpha beta pruning avoids checking branches that don't matter. So this algorithm avoids the branches which will never affect the final decision. That is branches. That is it will removes the unwanted branches. Okay, removes the unwanted branches and increase the speed of searching. Increase the speed of game by removing the unnecessary and unwanted branches. It guarantees the same result in minimax but with fewer computations. When compared to minimax algorithm, alpha beta pruning algorithm also will give the same result with fewer computations. Saves time, especially in large games trees like chess. Thank you.